By the way, I couldn't find last class's recording.
Okay, I'm going to post it together with today's lecture. Thank you. All right, so we will continue to cover chapter 28, graphs and applications. Last time we looked at this modeling graphs. We designed the interface and the class for unweighted graphs. So this is the interface for graph. So this contains the common operations for graphs. And here we have unweighted graph, and this is the concrete class, and we use this class to create a graph object. So when we have the concrete class, we need to have the implementation. So at this time, and we're going to decide how we're going to organize the data internally. So we decided to use the list for the vertices and use list of the list. So this is kind of two-dimensional. Use a list of list for the neighbors. So the neighbors are the adjacent edges, adjacent vertices, and these are all represented using neighbors. Now, please note that here the notation, we have the plus sign. So this is to indicate this is the protected. So we don't make it private. Normally, so this is what we do, we make private. But the only time we make it protected is for the extension. So later on, we have another class that is a subtype of unweighted graph. And that class is going to use to access the internal data here in this unweighted graph. So then we need to make it protected in order to be accessed. All right, so this is design, very common, and we provide a variety of ways to construct a graph. So you have this 5 constructors. In general, and the no-out constructor is always provided, unless you really have a specific reason you don't need it. And so this is a design strategy. So we have unweighted no-out constructor to create an empty graph. All right. So, and here's the test code, and we practiced last lecture. So you suppose you have this unweighted graph, the class is already implemented, and we can use it. And so this is how we use it, and we write a test code to use it. So this is it's the most situation is this: you have API, and so you study the API and you use the API, and the API is already provided and by the developer of the system. In this case, it's Java system, Java API. And so for us, when we study this subject, so we're going to play the role as both the user and also developer. So first, we're going to use it. We design it and use it, get the sense how it works. And now we get into implementation, how we implement it. So this is the implementation. So we look at all this implementation. So I'm going to get some of details later in this lecture. So if you have any questions, so please let me know. Do you have any questions when you read this implementation? All right, let's move on now. We'll get back. Okay, so let's move on now. So we get the implementation. So for now, see what I always do in this text for studying data structures. I think it's very important is to visualize the data structures. So for when we study binary search tree, we have the visualization. So the visualization is, look, it's in multiple ways, and one way is of directly from the book. We have the animation and see how it works in the tree. When you do a search, do an insertion, and do a deletion, see what happens. And the other way is we actually write the code in Java using JavaFX and to develop the GUI version of this visualization in Java. So same thing here in this for the graph, we're going to visualize it. So visualize it, and I'm going to jump to this diagram. So you can see this is the figure here, and this is the Java FX. It's a Java GUI. It displays the map. It's a graph. It's a vertices and edges. Okay. So you see the visual. Look. Now you can do more. You can say I'm going to add vertex. You just add some GUI components, allow the user to enter new vertices and new edges. So this is, you can do it. It's from the GUI interface, and you're gonna interact with the graph behind the scene, and then and display the graph back into the user interface. So this is, I think, what you can do in the future. You're going to encounter a lot of this. You probably will not directly use Java FX. You may use C++, the graphics library, use Python and graphics library, and using the JavaScript, the library. So all of this very similar in the way you write the code. Okay. So you just have to be familiar with the language itself, the specific language and the library, and you can write your code. So you're going to be on your own to do all this. So here in this book, we use JavaFX, and this is actually it's very I think it's flexible, and it's a very easy to learn, and also it serves the foundation for other GUI development. So if you want to get more into this, I think I really encourage you to get this to know JavaFX, and then you can extend this knowledge into other language for GUI development, and even come to this to the to develop the things on the mobile devices. Okay, on the iPad, on the iPhone, on the Android, on your Android phone and Android tablet. So all this, it's just some specific system you have to get familiar with, and then you can apply your general knowledge of GUI development and into this. Okay. All right. So how do we do this? All this. Look at this. And so for this, we're going to have, first, we're going to define this. It's the interface. It's displayable. So we're going to make this is the we're going to get x coordinate and get the y coordinate. So you can write here is public double and get x. So here is get y. So there's another thing here is when you display it, you need to know the location where you're going to display it in your user interface. It's XY coordinate. And then you're going to say, hey, I'm going to display a label, a name for the vertex. So this is something here is the name. It's public string and get. So here is get maybe something called name. So I think it's display the name. So let's look at this. So here, I think it's a name. So it's a get name. Display the name of the vertex. Okay, so displayable. We had this interface. It's, this is the purpose is you make the vertex is displayable. So the vertex, if it's displayable, it has this properties, the x, y coordinates and the name. So that's this interface is really for. Just like you have the interface comparable, you have that interface, it has the method compared to. So if an object is comparable and the object can invoke this method compared to compare with another object of the same type. All right, so here displayable. So now we're going to write this the GUI for display the graph. So here we're going to have this. When you write a GUI in JavaFX, you're going to always extend application. So I'm going to just do this. Just do this, extends the application. So here, but look, what I'm going to do is, before I do this application here, this is display US map. So this one here, this is why I'm going to actually use this, is the one is to extends application right here, extends application, display US map, extends application. So here, let's do this first. So we're going to have all this vertices. So these are the vertices. The vertices are the cities. So for the city, you create a city, has a name, XY coordinates, and the name XY coordinates, name XY coordinates. All right, these are all the cities right here. All right, so we look at the cities. All the cities here, we define the cities. Implements displayable. So these are displayable. So you have the get X, get Y, get name, all this here. All right, so now we're gonna back to this. We have the edges, the vertices and the edges. So the edges connecting all the vertices, and we create a graph. So this is a graph with using the vertices and edges using this constructor. And now we're gonna create this view. So this is the view. It's create a scene and using this here graph view. So the graph view is a it's a pan, it's a component. This pan is, we're gonna look at this right now. So let's look at this graph view. So graph view is a pan. It's a border pan. So you have this sections. It's a center and then surrounded by this 4 sides. So it's a top, a bottom, and left, right. So this is the east. Yeah. So this is the 4 sides. All right. So this is view. This is graph view. So we're gonna have this. The graph is here. So here is my graph. So here, look at the graph is displayable. So this is displayable. This is all the vertices are displayable. All right. So we're gonna group this all together. So using a group here, and you can see all this here, all this components, all these features, all these controls, and they are all in any other language. You're gonna see the same thing. They are very much the same. All right, repaint. All right, so here you have this So you're gonna send it to the center of this border pen. So this is the group, the group right here. So here's the graph, and so we have this. This is the group here. Repaint. So repaint. You see, when you repaint it, you're gonna put this here. Clear the group, and then you're gonna add all these things, the vertices, and in the specific location, and of this, add this. It's a small circle. You're gonna display it as a small circle for each vertex, and add it into this group. And this is the it's a label. It's there. Display the label like a city name, Seattle, San Francisco. This, and here is to draw all the edges. All right, draw all the edges. All right, so you can have all this together. So you're gonna have this is the sorry, this is the view here, graph view, and here is graph. Okay, and you're gonna display it. So this is to make it visible. So this is to set the scene and display it and show it. So all this. All right, so this is graph visualization. It is very helpful to understand the data structure. And all right, so now we're gonna look at the common operations for graph is traversal. You're gonna traverse all the vertices, and using this traversal, we can develop interesting algorithms. So graph traversals, there's two commonly used graph traversals, and one is called depth first, and the other one is called breadth first. The depth first is you start from any vertex and you go to one of its neighbors, and then continue and go down all the way as far as you can. But when you cannot go further, and you're going to backtrack, and then starting from that and continue to go back to other direction as far as you can. So this is the depth first search. All right. The other one is breadth first. Breadth first is this: you start from any vertex, and you have to now search all, visit all its neighbors, and before you go to the next level. So this is the level by level. It's called breadth first search. The result of this, you're going to generate the trees. So when you do a search, so you have one vertex, you go to next, right, and the next. So along this, it's becoming a tree. So that's what the result you have. It's a search tree. So we're getting it's a search tree from this search. So here's the search tree. We define this class to model a search tree. Search tree is going to be an object, and we need to model the objects and using a class. All right. So let's get specific. You're going to see this. I'm going to leave this. I'm going to keep this page and have another new tab here now. All right, let's get a new tab. All right, so here we get into depth first search. Depth first. All right, let's look at the depth first, and using this example here. And here's the graph. So let's jump to this graph here. This is the graph here. All right, we're gonna start from any vertex. Let's pick 0 to begin with. So 0. I'm gonna start from 0 right here. 0. Okay. So first we're gonna visit this 0, and then any of these neighbors, 1, 2, 3. All right. So let's pick 1. So it's going to be like this. Say, look, you can see this from 0 to 1. 0 becomes the parent of 1. It comes from 0 to 1. All right. So eventually this is the tree, is the starting point is the root, and 0 is the root. All right, from 1, and we can go to 2 and 4. Let's go to 2. So here, and now we continue. See the neighbors of 2, and this is 0 and 1. It's already visited, so the only thing it's not visited 3. So then we have to go 3. All right, from 3, and so that's the end. You cannot continue because it's 0 and 2 already visited. So now this is called a backtrack. So we're going to go back to its parent, 2. And then from 2, can you go further? No. So you can backtrack to 1. Okay. All right. So here we are at this 1. And for 1, we cannot go back to 0, it's already visited, and 2 is already visited. The only thing here left is 4. So we got a 4 right here. All right, from 4, nowhere to go. And go backtrack to 1, and then 1, nowhere to go further, and go backtrack to 0, and 0, nowhere to go. So that's the end. You know, that's called depth first search. Go depth first. All right. In contrast, so let's get to show you, I'm going to show you breadth first right away. So here is breadth first search. All right, so here, this is right here, breadth first search. Okay, so now let's jump to this diagram to look at how we do breadth first search. Breadth first search, let's again, we pick any vertex, we pick 0. All right, visit 0. So 0 now is visited, and we're going to visit all its neighbors. Okay, and 3, 2, 1, or 1, 2, 3 in any order. So you like, all right, so this is 1, 2, 3 visited, and then you're going to visit the neighbors. So visit the neighbors for 1, and the neighbors for 2, the neighbors for 3. So this is the only one here for this is like this. It's visited. All right, so this is called the breadth first search. Okay, now the result of the search, you're going to get a tree. It's called a search tree. The root is your starting vertex. All right, so this is back here. It's the depth first search. So this one is depth first search. So please look at this depth first search, and this one here is breadth first search. Okay, so here, back here, that depth first search. All right, so now we're gonna write the algorithm for this. We know the idea now. How do you describe the idea? So here's the idea, right? We know the idea. So you start the search, and so from any vertex, and then you go and to one of its neighbors, and starting from this neighbor, and then you go continue, right? All right, so we're going to describe it using algorithm. Okay, describe this how you do it. So before you actually write the code, so for solving any problem, you first have you have to have the intuition, and from the intuition you get the idea, and you're going to get all this from visualization. So you visual it, and then to actually you're going to describe it. We're going to use algorithm here to describe it. So here is the algorithm. So we have a graph. This is the G consisting of vertices and edges, and the starting vertex V. All right, so the output is going to be a search tree rooted at V. It's a depth first search tree rooted at V. All right, so we're gonna have this. It's going to be, you're gonna have this is a tree. All right, and this is the method. Depth first, starting from vertex V. All right, first, easy. V is the V. Okay, now how are you going to describe the rest? You're going to describe the rest is this. It's the for each neighbor W of V. All right, so please note that this lines here, 4, 6, 4, 5, 6, 7, it needs to be indented under the for loop. So here, for each W of V, if W has not been visited, we're going to set V as the parent for W in the tree. And now we're going to draw this, we're going to do it recursively and the depth first search on W. So that's the algorithm. That's how we're going to do it using recursion. We can implement it and you're just using recursion here. All right, so look at the key here is for each neighbor W of V. So we are going to do this is if W has not been visited, and we're going to visit W. We're going to set V as the parent for W, and now do it recursively. So real simple. You have this algorithm described, and this algorithm is going to be at the best for the next step is to implement it. All right, so now I'm going to open another. I think I just use this here. I'm going to go back here and this one right here. Maybe I should open another tab. So let's do another tab here. So I'm going to do another tab. So let's do another tab here. All right, we're going to implement it. So now we're going to see the code here. So right here, you're going to look at the Java code. So we're going to write it in Java. So we're going to look at the Java code for this. All right, so here's the code for the depth first search. So this is the right here, the depth first search. Okay. It's right here. This is all right here. I'm going to be right here. All right. Depth first search. Okay. So this so when you do this depth first search, you need to have this the supporting data structure. Here is all the vertices, and they have already been visited. So this is going to be in specific order. So we need to use data structure, use a list that keeps the order, the sequence. So we have this search order here. It's an array list search order. And then we need to know the parent. So who is my parent? How do you record this information? So we introduce another data structure that's simply this array. For each vertex, you have this parent to record my parent here. And now initially, and we're gonna set all this parent to 0 or to -1, okay? Everything is now the parent is -1, so because I don't know it yet, I haven't done any search. And now another thing is this visited, okay? So I need to know, how do I know if this vertex is visited? So either way is to use this Boolean array to denote it, it's visited or not. All right, with all of this, and now I'm gonna perform the depth first search using all this information, and with this, the overloaded, the method, and this one is starting from V, and here's the parent, search order is visited. All right, all this. So after all this is done, we're gonna have the tree. So the information about the tree is we're gonna return a search tree. So this search tree is defined right here. This is a search tree here, search tree. This is search tree here, search tree right here. This constructor is the root, parent, and search order. So here is a search tree. So we're gonna return a search tree. V is the parent, V is the root, and here's the parent, and here is the search order. All right, we got all this information in the search tree. All right, so this is the algorithm for depth first search. Is you have this V, so here's the parent, here's the search order, and this is visited, is visited. All right, so we need to have this is visited. Initially, this is not visited. This is by default, it's all false. All right, so we're gonna start from this V. So we're gonna add this V to search order. And now V is visited. So is visited. So here is visited, and V becoming true. All right, so now, and for each neighbor of V, so for each neighbor of V, now each neighbor of V, so you get V, get the neighbors dot get V. So here is the neighbor, it's the object from the neighbors, it's you get these H, E. So E is always the first vertex is V to W, V to W. So we get this W now, E dot V. So here is this is the difference here. Just please, this is kind of confusing. This V is not the same as this V. This V is here. In this H is you have UV. So please remember this H, we define this H class. So you have two data fields, UV. So that's the V here. Okay, so don't be confused with this V. They're different. All right. So so E dot V is actually E dot U is actually V here. E dot V is W. So W here. All right. So here we're gonna look at this. Is visited, brackets W. All right, if it's not visited, all right, so we're gonna visit it. If it's already visited, ignore it. All right, if it's not visited, so we're gonna make this, we're gonna visit W, and the parent of W is now coming from V, and then what do you do? Do it recursively. Depth first search starting from W this time. But we have this same, this is the parent, this array, and this search order list, it's here. All right, so that's the implementation. So if you go back here to look at this, this here, this one, look at the algorithm for this, look at the algorithm for the depth first search, it's right here, the depth first search. Okay, it's implemented right here, this code here. All right, so the look at this data structure and the time complexity. So what you have to do, you have to visit all the vertices and all the edges. So the complexity, it's at least it's order V plus W. But there is something here is we do this, all this checking here is, so what is the time to check is, so this is going to be, you look at the complexity, it's actually, so this is constant time, this is the constant time. So this is, so it's the time complexity, it's order of V plus W, and actually it's W is bigger than V. So it's order V, order of W. So the number of edges. So that's the complexity for this depth first search. All right, so that's the complexity. So this. Okay, so here's the test code from the book. You have the vertices and edges and construct a graph, and then you're gonna apply the depth first search and to see how we're gonna search this. And let's look at the result. And it's going to be displayed like this. You're gonna start, if you start from 5, Chicago. So this is the I think it's yeah, it starts from Chicago. It's look here. It's the one here. We're gonna start from Chicago right here. So from Chicago, yeah, from Chicago right here. So depth first search from Chicago, and Chicago is 5. Or you can use this graph dot get index. You have to use index for this Chicago. All right. So this is what we have. Here is going to be look like this. Here, this in the depth first search. You go to Chicago and go to Seattle and all the way down, and then go to San Francisco, Denver, Kansas City, and here go to New York and Boston, and then you have to backtrack. Okay, and then to Atlanta, Miami, Houston, and Dallas, and go all the way backtrack back to Chicago. So this is depth first search. Yeah. All right. This is very essential in graph algorithm because you can do a lot of things with this depth first search. You can answer a lot of questions. So here, applications of the depth first search. To detect whether a graph is connected. So you have all the vertices and you have the edges. How do you know the graph is connected? Connected means you're going to start from one vertex. You can go search for all the vertices. So that is to use the depth first search. You can accomplish this task. All right, and detect whether there is a path between two vertices, obviously. And you starting from one vertex, and you see if there's search reach to that the other vertex. So that's using depth first search. And you can find a path between two vertices. So this is, yes, the process can, you can modify the code, and so you can get the path. Actually, you don't have to do anything, is because we have the search tree. So let's look at the search tree here. This is the search tree. From the search tree, you can get the path starting from any vertex to the root. So this is there's a path, it's already there, get path is there. All right, detect whether there's a cycle in the graph. So you can so slightly modify the code, and to when you do a search, if you go back to the other, so there's a path. If you can go, need some modification to go back to the other the vertex you already searched. So it means there's a cycle. So detecting the cycle and finding cycle, this is a very similar task. There's another thing, it's called Hamiltonian path and cycle. This has application in some optimization field. So the Hamiltonian cycle, Hamiltonian path is this: is you have a graph, you're going to have a path to visit each vertex in the graph exactly once. So that's called a Hamiltonian path. All right, actually, all of this they're in the program exercise if you're interested, and please explore it. Okay, that is all for the steps for search. And next lecture, we're going to look at the breadth first search. But please note that the next time we meet, we're going to have the exam. Okay, so please just come to the exam 5 minutes before, and so we can all get situated and ready to take the exam. Any questions?
Wait, so are we doing the Zoom meeting during the exam again?
Yes, yes. We need to have the Zoom and turn on your camera. Okay.
Okay.
All right, any questions? Yeah, I'm gonna post all these 2 lectures, today's and last time's, this afternoon. All right, any questions, and please email me. Thank you very much for attending the class today. Have a great weekend.
By the way, the programming question for the exam, is it going to be like on a specific chapter or?
No, you should be prepared for all the from chapter 22 to 27, but I cannot cover every chapter, just you be prepared. Very similar to the work you already done. Yeah.
Okay.
Okay. All right, I'm gonna stop recording.